Section 2.6 is about something called differentiability. Differentiability, kind of a big word. What does differentiability mean? It means differentiable. What does that mean? It means has a derivative. We say that a function f is differentiable at some number x equals c, or a is another common letter to use here, if f prime of c exists, the derivative at c exists, i.e., the limit defining the derivative exists. And this should be a c there, not an x. C, f of c plus h minus f of c all divided by h. That's a c right there. In writing this, I am implicitly assuming f is defined on either side of c, so that this really is a two-sided limit. I'm allowing h to approach 0 either from the right or the left, and I get the same limit in either case. That's what differentiability means. The derivative exists. Pretty much, well, most of the functions that we've seen are differentiable. X squared is differentiable. X to the n is differentiable as long as it's defined seemingly or not. Actually, that's a little bit subtle. That's not quite true, actually. X to the n is differentiable certainly for all positive values of x. But there are subtleties, both when x is negative and when x is a fraction, or when n is negative. Both when x is negative and when n is a fraction is what I meant to say. Not quite. Both when n is negative and when n is a fraction. X to the n is what I'm talking about. There are subtleties there. Most functions we deal with are differentiable on their domains. Differentiable over their entire domains. The derivative exists for all values of x where the original function is defined, but not always. What are some exceptions to this rule? What are some functions that are not differentiable? Well, anytime a function has a discontinuity, that's one way it can fail to be differentiable. Functions are not differentiable. I'll just abbreviate that like this. They're not differentiable at discontinuities. In fact, there's a theorem that says if a function's differentiable at a point, it's got to be continuous there too. So if it's not continuous, it can't be differentiable. Because if it were differentiable, it would have been continuous. And that is the logic. I'll say it again. There's a theorem that I'm not going to state precisely, but basically the idea is differentiability implies continuity. Diff implies continuous, is what that shorthand means. If a function's differentiable, it's also continuous. Therefore, if it's not continuous, it's not differentiable. Because if it were differentiable, it would have been continuous, according to this theorem. Being a theorem, it takes proof. And again, I'm not stating it in a precise form. What other exceptions? Functions that are continuous, but have corners in their graph. Corners or cusps in their graph. What are examples of functions like that? The simplest example is f of x equals the absolute value of x. That's the simplest example. Where the function's graph has a corner or cusp, that is a location of lack of differentiability. The absolute value function has a graph that looks like a V. And it looks like a V no matter how close you zoom into the origin. It never looks locally linear. It never looks more and more like a straight line as you zoom in toward the origin, as long as you make your zoom window the same in both the x and y directions. Say that again. This graph of the absolute value of x always looks like a V as I zoom in toward the origin, as long as I make the scales, the zoom factor, you might say, the same in both the x and y directions. It'll continue looking like this and never change. At x equals 0, this function is not differentiable. F prime of 0 does not exist. F prime of 0 does not exist. It is differentiable everywhere else. The derivative is 1 when x is positive and -1 when x is negative. The derivative of the absolute value of x has a graph that is at -1 when x is negative and +1 when x is positive. At 0, it's undefined. Yes, there's a jump discontinuity, and you do not want to define f prime of 0 to be something else like 0. That's not a good choice to make unless you're doing calculus in a different way than we do things, which some people do, but we don't. There's something called a symmetric derivative, and I'm not going to say what that is. So that's one example where you've got a function that's got a corner or a cusp. Another example is f of x equals x to the 2/3 power, a fractional power. The graph of x to the 2/3 power looks kind of like a V as well, but it's kind of a curved V, looking like that. This point right there, people think of as being a corner in the graph. This point, people think of as being a cusp. I mean, you could call it a corner as well. Though I will tell you, as you zoom in closer and closer to the origin, the graph doesn't stay looking like a V. It gets curved more and more like this the closer you go toward the origin. But definitely doesn't look more and more like a single straight line that has a defined slope. You might say it looks more and more like a vertical line, but a vertical line has an infinite slope. So here, once again, f prime of 0 does not exist. It does exist everywhere else. And in fact, the power rule would tell you f prime of x here is 2/3 x to the -1/3 if x is not 0. That's what the power rule would tell you. You remember the power rule? Derivative of x to the n is n times x to the n minus 1. N is 2/3 here. N can be any number. 2/3 n times x to the n minus 1. 2/3 minus 1 is -1/3. What does the graph of this function look like? It does equal 2/3 times the cube root of x. The graph of the derivative, in this case, has a vertical asymptote at x equals 0. Looks about like that, it turns out. But yeah, there's a vertical asymptote at x equals 0, and f prime of 0 is undefined. There are some functions that are defined everywhere, continuous everywhere, and don't have corners or cusps, but are not differentiable at certain points. Say it again. There are functions, I'm about to show you one, that are defined everywhere, continuous everywhere. You can draw the graph without picking up your writing utensil, and don't have any corners or cusps, yet fail to be differentiable. How can such a thing be? Functions with vertical tangent lines. Vertical tangent lines. The simplest example being f of x is the cube root of x. x to the 1/3 power. Let's graph that with the technology here and see what we see. X to the 1/3 power, same thing as the cube root of x. You can take cube roots of negative numbers, right? Cube root of -8 is -2, for example. Why? Because -2 cubed is -8. -2 times -2 times -2 is -8. 3 negatives make a negative. So you can take the cube root of -8 and get -2. I'm going to go from -10 to 10 for x. Make my tick marks 1 unit apart. For y, I'll go from, we'll just say -3 to 3. What does the graph of the cube root function look like? Here it is. Looks pretty nice. I claim at 0, the tangent line, while you might say it exists, is vertical, and so its slope is undefined, and therefore f prime of 0 does not exist. How can you confirm that? Zoom in closer to the origin, making the scales, the zoom scale the same, say. Well, let's just do a square box near the origin. -1 to 1 in the x direction, -1 to 1 in the y direction. What do we see? Similar graph, but it's a little easier to tell. It's very vertical looking near the origin. I go in further, -0.1 to +0.1 in both directions. Where is it? Where is it? Where is it? Oh, you can barely see it anymore. It's so close to vertical now that you can hardly tell the difference between it and the y-axis there. And if we go in further, for sure you would not be able to tell the difference. It would look like it's the y-axis when you go in far enough. The tangent line you could say exists, but it's vertical. Slope is undefined. F prime of 0 does not exist. But it does exist for other values of x, and the power rule would say f prime of x is 1/3 x to the -2/3 if x is not 0. That's the power rule there. I'm teaching another class called Probability and Statistics, where we use models that often involve functions that are either discontinuous or not differentiable at points. Is that a bad thing? Well, I wouldn't say it's good or bad. It's not really a good or bad thing. It's just something you have to deal with sometimes. So this is the start of making you aware that such things exist. There are even functions. I'm not using the word even in the usual meaning of the word there. There are also functions, this is the most amazing thing, that are continuous everywhere. You might say you can draw other graphs without picking up your writing utensils, but differentiable nowhere. Can they be graphed? Google, give me an example of an everywhere continuous, nowhere differentiable function. The Weierstrass function. Don't say Weierstrass. Say I mentioned Weierstrass before, didn't I? Say Weierstrass. What in the world is that? It's a function that's everywhere continuous, but nowhere differentiable. Somehow you can draw it without picking up your writing utensil, but it's jagged everywhere. Now you might argue, it doesn't look like it's jagged right there. Well, that's because your eyes are deceiving you. You're not zoomed in far enough. No matter where you zoom in on this graph, at increasing levels of zooming, you will always see jaggedness. How do you make such a function? You have to make it with what's called an infinite series. In this case, it's an infinite sum of trigonometric functions of all things. And these, what you see over here, are approximations to the graph as the number of trigonometric functions gets higher and higher. It's an example of something called a fractal. Does it have any applications? Actually, it does. Fractals have lots of applications. You might say all of nature is fractal-like. Leaves, mountains, your heart, your blood vessels, your brain connections, they're all fractal-like. So it actually has a lot of applications. Okay, but at the moment, I'm just trying to make you aware.